Hello, welcome back to the second course in physics, and this is going to be the last lecture in this course, and I will be discussing the last topic on physical optics, which is the topic of diffraction. And in this lecture, I will introduce some historical background, introduction, and then we will discuss Fresnel diffraction phenomenon. We will also discuss Fraunhofer diffraction phenomenon. We will consider the horizontal slit first of all, and then we will consider light emerging from a circular aperture. We will also discuss the diffraction by a diffraction grating, and we will touch on certain topics such as dispersion and resolving powers and resolving power of the diffraction grating. And just as an introduction to this topic of diffraction, we have to remember that the term diffraction designates interference effects due to the presence of an obstacle or an aperture in the path of the light waves. And in a sense, diffraction is the interference of the wave with itself, as we mentioned in the last lecture. Historically, during the later part of the 17th century, Francisco Maria Grimaldi, a great scientist, has reported the first great discovery in optics, and that is when he observed that light emerging from a slit flares out, and thus the image looks wider than it would be if we assume geometrical optics. So he realized that the image is wider than it should be. Light flares out, making a wider image. And also, colored fringes were also observed around the borders of the image. Grimaldi explained these effects and these observations as due to diffraction of light. That was a great discovery and a great explanation and interpretation in the history of optics. Newton, who did not believe in the wave theory and that diffraction can happen, he had to explain the observations, however, and the way he explained them is that he thought that these effects are due to forces exerted on light corpuscles as they pass the edges of the slit. It's just simply an interaction force between the corpuscles of light, the particles of light, and between the edges. And that's how he thought the explanation could be. The second great discovery in optics, in the history of optics, began in 1802 by Young's double-slit experiment. Young also, in addition to interference of light in his double-slit experiment, he also observed light and dark fringes near the edges of the geometrical shadow of light emerging from an opaque object, passing an opaque object. And these discoveries have laid the way for the wave theory of light, and from and the other works that have been done, great works in this field, started with Fresnel's work. Augustin Fresnel in 1814 has observed these fringes near the edge and demonstrated that the fringes are the same no matter whether the edges of the obstacle are sharp or blunt. And this seems to put Newton's theory on the shelf. And it was in favor, this finding was in favor of the wave theory. In 1819, Fresnel submitted a paper during a contest that was laid by the French Academy of Science. He submitted a paper to the French Academy of Science describing his diffraction experiments and the wave theory explanation of his results. However, Poisson, being a Newtonian in belief, he did not believe in the wave theory, pointed out that if he was challenging the theory of Fresnel, that if Fresnel's theories were correct, then we should observe a bright spot at the center of the shadow of a sphere. That was a real challenge. The bright spot at the center of the shadow of a sphere was indeed observed. And Fresnel demonstrated this spot, which was later called Fresnel bright spot. Some other people call it Poisson bright spot, although he did not believe in wave theory, but he's the one who suggested that we should see it due to the bending of the waves around the edges of the sphere. Fresnel diffraction is observed as follows. If we have a slit and this slit is illuminated by light, then we can collect the image of the slit on a screen. As we start moving the screen away from the slit, then we start, at a certain point, we start seeing fringes around the edges of the slit. This pattern is called the Fresnel diffraction pattern, and this is observed when the screen is near the slit, and that's why it's called the near field diffraction. That is Fresnel diffraction. There is another type of diffraction that we can observe, which is Fraunhofer diffraction. That is, if we get farther and farther from the slit until we are at a very large distance. We should keep in mind that we shouldn't get far away. We shouldn't get more than the coherence length of the wave trains. But if we get far away, far means the distance is very large with respect to the opening of the slit itself. If we get far away, then the rays would appear parallel, and the fringes or the diffraction pattern that we observe is called the far field diffraction. And in this case, because we are far away from the slit, the intensity of light becomes very dim, and maybe we cannot see the pattern, because simply, not because it doesn't exist, but because the intensity of light as far away distances from the slit is very dim or very weak. So people use lenses in the way in order to avoid the loss of light intensity. And now if we consider for Fraunhofer diffraction, if we consider Fraunhofer diffraction and we consider a horizontal slit, the horizontal slit is going into the page. This is the opening or the width of the slit that we see. Here we are using a lens in order to avoid loss of intensity, and the width of the slit is d. So we have d over 2 above the center and d over 2 below the center, and we have a wave front that is incident on this slit, and the optical path length relative to the ray from the slit axis, this ray that's coming from the slit axis or from the center of the slit, we measure the path, the optical path relative to this ray, so if this is called L, if this path length is called L, cursive L, then the optical path of any ray is simply L minus x, where x is the position of the ray where it is emerging from the slit, minus x sine theta. So on the upper part where x is positive, the path length or the length of the ray is shorter, and in the lower part of the slit, x is negative, and then the rays are travel farther distance, as we notice. And we use the Fresnel assumption. Fresnel's assumption is that the amplitude of a secondary wavelet that is produced by from a given part of the slit, the amplitude of this secondary wavelet is proportional to the area of the corresponding radiating wave front. So if we have a portion of the wave front that is radiating a wavelet, the amplitude, which is the intensity is proportional to the amplitude, of course, is proportional to the area of that wave front, of that part of the wave front. So if we consider that the slit is uniform in length, and we are dealing with the width, if we take an element of this slit as dx, so dx over the whole distance, the whole opening of the slit, dx over d is the proportion of the area of the element of the wavelet as compared with the total wave that is passing the slit. So dE, the amplitude that is produced by this element of wavefront is simply equals to the ratio dx, which is over d, which is the ratio of the area of the element radiating this wavelet, divided by the total area, which is the total wave, times the total wave amplitude. So this is the amplitude of the wavelet. Making this assumption, we can calculate the amplitude over the whole slit by integrating over x. So we have E is equal to integral from minus d over 2 to plus d over 2 E naught over d times this function that gives the phase of the wave, e to the j, which is the complex number root minus 1, times, in parentheses, omega t minus kl plus kx sine theta dx. So if we perform this integral, we get E is equal to E naught e to the j omega t minus kl, which doesn't have an x in it. And then if we integrate the remaining, which is e to the kx sine theta with respect to x, and we integrate it from the limit minus d over 2 to the limit d over 2, we get this factor, which is sine 1/2 kd sine theta over 1/2 kd sine theta. This is the amplitude E. And if we want to get the intensity, we simply square the amplitude, and squaring the amplitude would eliminate this complex number in the front, e to the j omega t times e to the minus j omega t is simply equals to 1. So this complex number is removed, and we are left with the intensity I is equal to I naught times sine squared 1/2 kd sine theta divided by 1/2 kd sine theta all squared. This intensity pattern looks like this, where at theta equals to 0, we have a maximum intensity, and then we have minima, set of minima, and we have other maxima that we call secondary maxima. These are the secondary maxima. These secondary maxima seem to have much lower intensity than the principal maximum at theta equals to 0. And then the pattern diminishes as we go farther in sine theta. And if we take the numerator equals to 0, the minima in the pattern are determined from the fact that the numerator is equal to 0. This gives us minimum intensity, and that means if the numerator is 0, that means we have to remember that we have sine squared of this quantity, 1/2 kd sine theta. So if sine of this quantity is 0, that means this quantity, 1/2 kd sine theta, must equal to an integer number of pi. If this is equal an integral number of pi, then the sine of this quantity is 0, and we get minimum. That means the condition for the minima, for the locations of the minima are located at sine theta equals m lambda over d, and where m here is the index that's running 1, 2, 3, and so on. The secondary maxima that we have just shown in the pattern, the secondary maxima occur at sine theta is equal to m plus 1/2 lambda over d, because this is equal to 1. This is the maximum quantity. So the intensity of the secondary maxima, Im, are given by Im over I naught is equal to 1 over pi square times 1 over m plus 1/2 square. That is from the previously developed relation, and putting this value for sine theta, we get this relation for the intensity of the secondary minimum. Now, the principal maximum, as we said, occurs at theta equals to 0. And this principal maximum occurs at theta equals to 0 with an intensity equals to I naught. This can be seen by, of course, if you look at the intensity equation, it gives, if you put simply theta equals to 0, you can't do that because you will get 0 on top of, and 0 in the numerator and 0 in the denominator. And you cannot divide 0 by 0. In order to evaluate that quantity, you have to apply L'Hopital's theorem. You derive maybe second times the numerator, and you derive the denominators twice, and then in the second derivatives, you can put theta equals to 0, and then you get the result, which is at theta equals to 0, you have the maximum intensity of I naught, and thus the principal maximum occurs at theta equals to 0 with I equals I naught. The first minimum from the previous condition occurs at sine theta equals lambda over d. That's where the first minimum occurs. Then the angular half width of the central maximum, this central maximum has a width, the full width, actually, the full width of the angular half width of the central maximum, half of its width, is in the case under the condition that the opening of the slit is much larger than lambda. In this under this condition, we have lambda over d is small, such that sine theta is of the order of the angular spread itself, which is delta theta, we call it, the angular spread. And this angular spread, or angular half width, is simply equals to lambda over d. So the central maximum spreads into an angular position of lambda over d to the right and minus lambda over d to the left. So the total width of the central maximum is simply 2 lambda over d, but the half width is lambda over d. That's the angular spread of the central maximum. And here we mention Rayleigh's criterion for the resolution. how can we resolve two objects that are close to each other? Two images of two slits, for example, are resolvable, and we see them as two images, two separate images, under the condition that if the maximum of the second object is coinciding with the first minimum of the first image in the diffraction pattern. So we look at the diffraction pattern of the two images, and if the maximum of one of them is on the first minimum of the second one, so we will see the two central maxima as separated, as resolved, and we can observe them as separate objects. So accordingly, the angular separation of the two sources must be at least equals to lambda over d if the two images if the two sources of the diffraction pattern are at an angular separation of at least that much, lambda over d, then they can be resolved, and we can see them as two different images, just like this. Like here, they are barely resolvable, and these are barely observed as two different images. Here I'm putting them as spheres, as circles, but we're not dealing with circular. For this condition, we are not dealing, lambda over d does not give the condition for the resolution of two circular images. It gives the condition for the resolution of two horizontal slits, actually, or images which are in the form of horizontal slits. But this is just for a demonstration. This is the resolution according to Rayleigh's criterion. If we have a circular aperture, we can see also Fraunhofer diffraction from a circular aperture in a similar way. The location of the first minimum, however, it requires more elaborate calculations in terms of the integral, and it's a little bit more difficult than what we have done for the slit. So in the case of the aperture of diameter d, the location of the first minimum after we perform the right integral is given by sine theta is equal to 1.22 times lambda over d. It's just slightly different from the formula for the horizontal slit. It's multiplied by 1.22. So this is the condition, and Rayleigh's criterion for the resolution of two images here with circular shape is given by theta c is equal to 1.22 times lambda over d. This is how far away the angular distance between two images should be, minimum. It should be 1.22 times lambda over d in angular separation. They should be that far away in angular separation in order to be resolved and to be observed as two different images. And now we get to discuss the diffraction grating and another topic. The diffraction grating consists of a sheet where it has a number of slits, a very large number of slits, and it can be produced as a sheet of glass, for example, with lines drawn on it that would work like a slit. So consider, for example, that we have such a sheet with n different slits. So we have n different sources, capital N different sources, and if we consider that these sources are coherent because they produce point sources from the same wavefront. So these are n coherent beams, and they have equal amplitude E naught. Each one of them has an amplitude of E naught. And we consider the problem of superposition or interference of these sources, or these light waves emerging from these n slits or openings. The phase difference between two successive beams, consider two successive beams and emerging from two successive slits or openings, and each two successive slits or openings are spaced by a distance d, small d. So the phase difference between two successive rays is as obtained before, is equal to kd sine theta, where d sine theta is the optical path difference. And in order to convert the optical path difference into an angular phase difference, we have to multiply by k. So phi is equal to kd times sine theta is the phase difference between two successive beams. And now that means the first beam and the third beam, they have twice this much, 2 kd sine theta. The first beam and the fourth beam has 3 kd sine theta, and so on. So this way we can have the phase difference between any beam and any number, any beam at any other position emerging from any other slit. And the total electric field amplitude is can be calculated, and we will use, instead of the sinusoidal form, instead of using the formula like E is equal to A times cosine omega t, or E is equal to A times sine omega t, rather than using this form for the electric field, we'll use complex numbers. It's much easier to deal with complex numbers. So we set like E is equal to E naught times exponential to the I to the j omega t minus some phase, and then we can take the real part of this complex number. The real part will give the real electric field. So we can deal with complex numbers with, and then we can take the real part of that in order to get the electric field. And this here is the electric field is simply equals to E naught times e to the j omega t times the summation, because we have all of these electric fields emerging from the different slits. And if we start with the first slit at n equals 0, and we end up with the last one at n, capital N minus 1, the phase difference of the first one with itself, of course, is at n equals 0 is 0, and the phase difference of the first one with the second one, n equals 1, so n equals 1 we set here. So the phase difference is simply 1 times phi. Phi is the one that we have just mentioned, which is kd sine theta. And when we add up the amplitude coming from the from n equals 2, from the third slit, then n equals 2, and the phase difference is 2 phi, 2 times kd sine theta, and so on. And we add up all of these contributions. This way we calculate the total amplitude of the electric field. And adding up this is simply a geometrical series, and the summation of e to the minus j n phi is equal to 1 minus e exponential to the minus j n phi, capital N phi, divided by 1 minus e to the j phi. And this is multiplied by e naught exponential to the j omega t. And we have to manipulate this term in order to make it simpler. It looks simpler. After manipulating this term, and we square the equation all through in order to get e square instead of e, and the e square is proportional to the intensity. So this gives the intensity I is equal to I naught times sine squared capital N phi over 2 divided by sine squared phi over 2. And here remember that this n is the number of the openings or the lines in the diffraction grating. Now Now, this is a general expression that is true for any number of slits. And if we set n equals to 2, then this will give us Young's double slit experiment, because in Young's double slit experiment, it's like a diffraction grating with n equals 2. We have 2 slits only. So if we put n equals 2, we will have I is equal to I naught times sine squared phi, n equals 2 over 2 is equal to 1. Sine squared phi over sine squared phi over 2. And now this gives the right intensity as for the case of the in the case of Young's double slit, because phi, putting it as kd sine theta, and at the location of the maxima, we have to use L'Hopital's theorem, derive this the numerator and the denominator twice. We will get this factor 1 over 2 squared here, and 1 over 2 squared, that's 1 over 4, will give us 4. So I is equal to 4 I naught, as we have obtained in Young's double slit experiment. Now, for phi equals plus or minus 2m pi, 2 successive applications of L'Hopital's rule gives the intensity of the principal maxima. So we have a number of principal maxima. It's not like in the case of diffraction where we have one principal maxima. Here we have several principal maxima. And we have the limit as phi equals 2m pi at the location of the maxima, as we mentioned, is equal to I over I naught, which is equal to n squared. This is by using L'Hopital's theorem. I just mentioned a few seconds ago that when we apply n equals 2, then do L'Hopital's theorem, and we get the limit of I over I naught in the location of the maxima is equal to 4, which is n squared. N, in this case of Young's double slit experiment, n is equal to 2. 2 squared is equal to 4. And that is the relation between I and I naught, as we have derived, which is the same result as we obtained in the discussion of Young's double slit experiment. Now, the positions of the principal maxima are obtained by phi is equal to kd sine theta equals 2m pi. These are the positions of the principal maxima. And here we can set that means if we write instead of k, if we can put 2 pi over lambda, then we get the condition d sine theta is equal to m lambda. That gives the position of the principal maxima, where m is equal to 0 or 1 or 2 and so on. So we have a set of maxima, and I is equal to I naught times sine squared n phi over 2 over sine squared phi over 2, which is the result that we have obtained before, shows a set of maxima, as we mentioned. And between each pair of successive maxima, there are n minus 1, capital N minus 1 minima, and these minima occur at phi equals 2m pi plus or minus 2m prime, where m prime is another integer, 2m prime pi over n. So if we put this value for these values for phi, we will see that this gives this relation gives minima. So these are locations of the minima between 2 successive maxima. And here m prime is equal to either 1, 2, or 3, and so on. So that way we located the principal maxima obtained by the diffraction grating and the minima between each two maxima. And since we have a number of minima, n equals 1, n minus 1 minima between two principal maxima, and between each two minima we should have a maximum of intensity. That means in between the principal maxima we have secondary maxima, which are between the minima in between, and the number of these secondary maxima is n minus 2. And these secondary maxima have much less intensity than the principal maxima. And these occur, these secondary maxima, they occur between each two minima. And remember that the minima occurred, the minima occurred at 2m pi plus or minus 2m prime pi over n. So between each two minima occurs a secondary maximum. So these occur at 2m pi plus or minus 2m prime plus 1, all multiplied by pi over n. These are the locations of the secondary maxima between each two pair of principal maxima. Now, as for the angular half-width of the central maximum, the half-width of the central maximum delta theta is accordingly equals to lambda over nd, and if we take into consideration the Fraunhofer diffraction from each slit of width a, the intensity is given by I is equal to I naught sine squared 1/2 Ka sine theta over 1/2 Ka sine theta all squared times this this factor in parentheses, which is sine squared 1/2 n capital N Kd sine theta over sine squared 1/2 Kd sine theta. Now remember that we have derived the first term, which is sine squared 1/2 Ka sine theta over 1/2 Ka sine theta all squared. We have derived this from by deriving Fraunhofer diffraction from a single slit. So this is the diffraction pattern that is due to diffraction from a single slit. And this term, which is in parentheses, this is the term that is coming from the superposition of the signals that are coming from the different slits themselves. So the multiplication of these two terms would give the total intensity modulation in space of the signal. So this complicated looking result gives the intensity variation of the light in space. And now we go for the problem of the dispersion of the grating. Another property of the diffraction grating. The dispersion is simply d theta over d lambda. It's how we separate the different wavelengths in space. And if we consider the relation between theta and lambda, d theta over d lambda differentiated is equal to simply m over d times secant theta. The dispersion thus increases with 1 over d. The dispersion, meaning the angular distance between two different values of lambda, gets larger as d gets smaller. So if we have these slits closer and closer to each other, so they can resolve the different wavelengths better. Thus, if we have diffraction grating with openings that are very close to each other, if we if white light falls into such a diffraction, then it will split into its different colors in a very well-resolved manner. The half angular width delta theta of the principal maximum at angle theta is given by, we just used the previously determined formula, sine theta plus d theta, where delta theta is the angular width of the principal maximum, is simply equals to m plus 1 over n times lambda over d, because delta theta was determined previously. And delta theta, in the case delta theta is small, we can expand this trigonometric function as being sine theta cosine delta theta, and delta theta is small, so cosine delta theta goes to 1, plus cosine theta times sine delta theta. And sine delta theta is equal to delta theta because delta theta is small, so we get sine theta plus delta theta cosine theta, and that is equal to m lambda over d plus lambda over nd. And we have sine theta is equal to m lambda over d, can be cancelled out. Sine theta is equal to m lambda over d, and then we are left with the relation delta theta is equal to lambda over nd times secant theta. And from the dispersion relation, delta theta over delta lambda is equal to m over d secant theta, from the relation that we have developed earlier, a little bit earlier. We get, dividing these two relations, we get what we call the limit of resolution. And this limit of resolution is defined as delta lambda over lambda, which is equal to 1 over m times n, capital N, which is the number of lines. And the resolving power is defined as lambda over delta lambda is equal to m times capital N, which is the multiplication of the number of lines in the diffraction grating times the order of diffraction that we are dealing with. This is the resolving power of the diffraction grating. At this point, I would like to end this lecture, and I thank you for your attention.